Hello everyone, this is lecture 11 of course BE544. In the previous couple of lectures, we have dealt with simple CNN and pre-trained models, and we have defined a set of hyperparameters such as the batch size, the appliance of dropout and the dropout ratio, and also data augmentation, aiming to improve the performance and decrease the level of overfitting and underfitting. The target of the training process is the optimization of the learnable parameters, which are the weights and bias. But in the written code, we have defined the hyperparameters manually, and by changing these hyperparameters, it can improve the performance from a level to a higher level. So instead of defining the hyperparameters manually and then running the experiment, and after that changing the hyperparameters to new hyperparameters and rerunning the experiments again and doing that multiple times, we can use a framework that can handle that task instead of us. The umbrella of tuning the hyperparameters is called hyperparameters tuning or optimization. There are multiple frameworks that offer that capability of tuning these hyperparameters. One of those is called Keras Tuner. Keras Tuner is a library for hyperparameters optimization for Keras models. So this framework or package is specific to Keras applications and models. This library simplifies the process of finding the best set of hyperparameters, we can call it optimal or near optimal, by providing a convenient and efficient way to search through the hyperparameter space. And the meaning of hyperparameter space here means the range of values that we are exploring. For example, we are searching for the best batch size, whether it's 4, 8, 16, and so on. Examples of the hyperparameters as mentioned: the learning rate, batch size, number of layers, and the number of units in each layer. As shown in the right figure, you can install Keras Tuner using the pip command pip install keras-tuner. The tuning process or the Keras Tuner process is displayed in the following figure. First, it selects a combination from the hyperparameter space. For example, it can pick a batch size of 4, a dropout ratio of 40%, and appliance of data augmentation, and then starts to train the model based on X-train and Y-train. And after training and fitting the model is evaluated on the validation subset. This process is applied for multiple iterations or until convergence, and after that, the Keras Tuner or the framework will report the best model and the corresponding evaluation on the testing subset. So simply, it's a loop that each time selects a combination of the hyperparameters, train and evaluate the model, and this loop will continue for a specific number, for example 10 iterations or 10 trials, and it will maximize the benefit of it. This means it will report the highest performance combination. Keras Tuner utilizes 3 techniques: random search, Bayesian optimization, and hyperband. And this is a comparison between each of them, and you can select the technique you are targeting in the configuration during writing the Keras Tuner script. So for the random search, it randomly samples the hyperparameters. For the Bayesian optimization, it uses a probabilistic model to choose the hyperparameters, while the hyperband, it combines between random sampling and successive halving. And for the conversion speed and conversion means reaching the optimal hyperparameters in a reasonable time. For the random search, it's slow. For the Bayesian optimization, it's faster. And for the hyperband, it's fast. So, depending on the speed, the Bayesian optimization wins. But mainly, selecting between of them will depend on the use case or the application in hand. For example, the random search is good for small search spaces or fewer trials, while Bayesian optimization is suitable for expensive models where fewer trials are better, and Hyperband is ideal for large search spaces and high dimensional searches. So, depending on the use case in hand, you can pick the most suitable to do. To do that programmatically, we will utilize the previous code and include the tuning of hyperparameters in the code. After installing the Keras Tuner, you can import it using import Keras Tuner as KT, short for Keras Tuner. Then we define the configurations, then define the calculate all metrics, and this function, as mentioned in the previous code, computes the micro, macro, and weighted averaging for set number of performance metrics. To use the Keras Tuner, you need to build a set of functions for an easier implementation. First, you need to define a function that will return the search space. Let's call this function model hyperparameters builder. First, in this function, you need to define an object called HP refers to hyperparameters. It's an object of the class hyperparameters in the KT library. Then you will define in that HP object the search space you are targeting. After that, you will return that object. You can define that by using the function choice and define the key, comma, and the different options that you need the library to search in. For example, the base model, we are searching between MobileNet version 2, Inception version 3, ResNet 50, VG16, VG19, and exception models. For example, batch size 8, 16, 32, and 64, and so on. After that, you need to define another function called model builder that accepts the search space, and inside that function, it will get a choice from the search space and will work by fitting and evaluating the model based on that choice. In this function, we are creating the base model, and we are defining here the same configurations, include top, weights, and input shape, and the input shape is defined in the top of the code. And it's worth noting that we are defining the base model as strings. So we need to convert the string to an object that reflects the base model. So to do that, we created a dictionary that maps between the name of the base model and the corresponding object. And these applications or objects are accessed from the applications module. Then we got the choice of the base model, which is a string, and access the dictionary, and this dictionary will return the corresponding object of the pre-trained model. Then we froze the layers of the base model and applied a set of dense layer and a global average pooling layer. And if you remember, we got dropout and we didn't omit it from here, but we made a condition: if you need to apply a dropout, then insert at the index 4, which is between this layer and this layer, and insert at index 3, which is between this layer and this layer. And we started from 4 or the bottom to top, because if we swapped between them, the indexing will change. After that, we created a sequential model using the list of layers and compiled that model. Then we printed the summary and returned the model. So this function will return the model and build it to be trained and evaluated. Inside the compilation, you will notice also we have accessed the optimizer, which is also a string similar to the base model. So we need to create another dictionary for mapping between strings and the corresponding optimizer object and accessed it here. The optimizer will need a learning rate, so we define the learning rate as a changeable hyperparameter here. Then we created a third function called model tuner, and inside this function we got the hyperparameters by calling the model hyperparameter builder, which is the first function we discussed in this code, and access the hyperband, which is the third approach. You can also access the random search and Bayesian optimization instead of the hyperband. And we applied the model builder function, applied the hyperparameter space, and our objective to maximize the validation categorical accuracy, and we define the maximum epochs and the downsampling factor for the number of epochs, and the directory and the project name where this tuner will save the trials. And the idea behind factoring here is that the Keras tuner will not execute each trial for the number of epochs, which is 100 here, but instead it will begin by trying a set of trials for about 5 epochs or 6 epochs, and then in the next trial it will increase the number of trials to 20 and so on until it reaches 100. And each time it will collect the top of them to continue and survive until the end. Then we define the train, validation, and test generators, executed the tuner function, and the tuner function or model tuner will return the object called the tuner. And then we started to search by defining the training and validation generators or data, define the callbacks, and made the verbose to one to print and display the summary and output on the command window. Here we defined only early stopping and reduced learning rate on plateau and omitted others because internally it will store the trials it executed. By running this script, it will start to search in the hyperparameter space, and at the end it will report. And to report the best hyperparameters, you can access the tuner dot get best hyperparameters, and you are defining here one, which is the top one. And to print the dictionary of the best hyperparameters, you accessing best hyperparameters, which is this object dot values. After the completion of the code, this is the directory where it stored the trials, and this is the output on the command window. And as you see here, the best hyperparameters is printed as a dictionary. For example, the base model is MobileNet version 2. And the advantage of using Keras Tuner or a framework of hyperparameter optimization is the ability to resume the tuning process. For example, if you started to select the hyperparameters using Keras Tuner, and at a certain point you halted and closed the command window before the completion of the execution and tried to rerun the code again, it will start at the last point, not from the beginning. This is because it stores the history and trials locally. And this happens also if you completed the tuning process and forgot to print the best hyperparameters and wanted to print it again. You can run the code again, and if the number of trials is completed, it will not rerun again or tune the hyperparameters again, but instead it will reload the tuner from a file and check if it exceeds the number of trials or it reached the maximum number of allowed trials. It will not tune again, but instead it will complete the rest of the code. And this means this search function will be executed only if you didn't reach the maximum number of trials. And you are not limited only to access the top one. You can access the whole history. Simply create the tuner, without the search function, and then to get, for example, the top 5 hyperparameters alongside the best validation accuracies, you can do that using get best hyperparameters and define the number of trials. In this case will be 5. And you can also retrieve the results of the top 5 using the function get best trials from the Oracle object from the tuner and define the number of trials, and then use both of them to print the hyperparameters and corresponding results by looping on them. Here we are enumerating on the top 5 best models, printing the index of it or the number of it, and then for each element in the dictionary of the hyperparameters, print the key and value, and finally print the score or the validation accuracy of it. And here we are talking on the validation accuracy because in the tuning process we define the objective here is the validation categorical accuracy, so it will return the validation accuracy. To do that in a single line, you can use the results summary and define the number of trials, and it will do both of them together. By executing the code, it will start to reload again from the history and print model 1 to model 5, defining the hyperparameters and the validation accuracy. And if you are printing the summary, it will print the summary and print the objective, which is maximizing the validation categorical accuracy, and start to print the summary of the top 5 hyperparameters. As you see, these are the same results. It will continue until it reaches the last of the top 5s. Based on the best hyperparameter, you can use these configurations to train the model for a larger number of epochs. Instead of 100, you can train it for 500 or 1000 because you reached a set of hyperparameters that can be optimal for this dataset. You can do that by building the model and passing the best hyperparameters, which can be accessed from get best hyperparameters function, and then fit and evaluate the model manually as we did in the pre-trained model and simple CNN, and continue the rest of the code by loading the weights as the best checkpoint, print training validation and testing results, and plotting the confusion matrix and learning curves, and finally calculating all of the metrics and printing them. By executing that code, we can reach the following results, and this is the corresponding confusion matrix. Another tuning framework is called Optuna, which is an open source hyperparameter optimization framework designed to automate the tedious process of hyperparameter tuning in machine learning models. And this framework is not limited to Keras application, but you can use it in many applications that require optimization. You can access the framework from this website and install it using the pip command. Optuna can be integrated with TensorFlow, PyTorch, and scikit-learn packages, and many others, as mentioned, with any problems that require optimization. Internally, Optuna employs a sophisticated search algorithm called Bayesian optimization, similar to Keras, but Keras implements another two techniques, as mentioned, hyperband and random search. Using Optuna and Bayesian optimization, it may lead to faster conversions on optimal hyperparameter values compared to traditional grid search or random search methods. Grid search means you are trying to get all of the combinations in the search space and try all of them until you reach the best. Grid search can be suitable for a small size application and small search spaces. Imagine that if you have 3 hyperparameters where the first got 5 values, the second is 10, and the third is 3. So to apply grid search, you need to apply all of the combinations between them, and this will result into 150 trials. Bayesian optimization, as mentioned in the Keras Tuner, can handle complex hyperparameter spaces, including continuous, categorical, and conditional hyperparameters. This will allow users to define. Additionally, Optuna got a pruning mechanism which can enhance efficiency by stopping unpromising trials early, and based on that, it can save the computational resources and the time. To work with Optuna, you are importing it, import Optuna, define the configuration similar to the previous code, calculate all metrics and model builder, and then define a set of functions that will facilitate the process of tuning. So let's start by the objective function first, and here it accesses an object called trial, which will be provided by the Optuna framework. Here we access the function called suggest categorical that will select between an element from this list, and the key will be base model, as we did in the Keras Tuner, but here in a different function. And the same for the optimizer, dropout, batch size, apply dropout, and learning rate. And suggest categorical will pick from a list, but suggest float will get a number from a low value to a high value with a logarithmic function. You can also, for the learning rate, define specific learning rates, but in this case you will use the suggest categorical function. Then we build the model using the model builder, which is the first function here, and applied the selected hyperparameters, and based on these, in this function it will use them to get the corresponding optimizer, start to build the base model and the corresponding layers with the dropout similar to the previous code, and compile the model and return it. After that, we will need the train, validation, and testing generators to start the fitting and learning process. And this happened from this function, create data generators. Inside this function, we encapsulated the generators in it, and then returning the objects of the generators. Then we started to fit and validate the model based on these selected hyperparameters. Then we evaluated on the testing data and returned the second element, which is the validation categorical accuracy. And we encapsulated the code in try except in case of an error occurs. In that case, we will return a 0 value. This function, which is called objective function, will be called using the optimize function from the study object. And to create the study object, we access the Optuna package and created a study, and we require to maximize the objective function and define the name, and to load the study if it exists in case of we close the code suddenly, or we wanted to rerun again but in another day or another time, we set it to true. And we defined here a database file where the study will store the history in it. If we didn't do that, it will store in the memory, which means we cannot reload again from the memory if you turned off the code or restarted the computer. We defined here the number of trials. We set the show progress bar to true to indicate which phase are we in as a counter from 1 to 10. And after each trial, we are applying garbage collection to remove the cache from the memory. And we set 7200 seconds as a timeout for each trial. And we set the number of jobs to 1 to avoid parallel processing in case if the GPU cannot handle that on your PC or computer. So this function will execute the objective function 10 times, aiming to find the top one of them. You can also utilize the Optuna library for any other tasks by simply defining all of the work inside the objective function here, and you are required at the end of this function to return a value. So whatever you are doing here, you just need to return a value at the end of the code, and it will judge the performance by maximizing or minimizing based on the returned value here. At the end of the execution, we are printing the best trial and the corresponding hyperparameters, and these are the corresponding results. The Optuna, as mentioned, will store the records in a database, and it will print the corresponding hyperparameters for the best trial. To assess the history, you will need to create the study, but you are not required to run the optimize function because we have already run it and optimized for 10 trials. Based on the study, it will load from the database file. Here we printed again the best trial, and here we printed the top 5 trials by accessing the trials from the trials attribute. We looped on the top trials. For each trial, we printed the corresponding validation accuracy using the value, and we accessed the hyperparameter using promise.items. Promise here is a dictionary, and printed them. By doing that, we got the following results. It prints the best result and top 5 trials from here to here and then to here. And as you notice, the performance is not so high, similar to the Keras Tuner, because here we only executed the code for 5 epochs. In this code, we changed the 100 to 5 just for the presentation, but if you need to tune and execute the code, you need to change the 5 to a reasonable number, for example 50 or 100. After getting the best hyperparameters, we can use these hyperparameters as we did with the Keras Tuner and execute again the model, but for a larger number of epochs. Here we set it to 100, for example, and use the model builder function as we illustrated, create data generator as we illustrated, and the same for the objective function. And here we removed the optimize function because we have already optimized it, and then we built the model, passed the parameters, got the generators, and executed the rest of the code that contain training, validation, loading the best checkpoint, evaluating the model on training, validation, and testing, plotting the curves and the confusion matrix, and finally printing all of the metrics. And these are the corresponding results and confusion matrix. So in this lecture, we have dealt with the concept of hyperparameter optimization and dealt with 2 frameworks or libraries called Keras Tuner and Optuna. Keras Tuner is specific for Keras applications and models, while Optuna can be utilized for any optimization task, including Keras, scikit-learn, and PyTorch packages. We dealt with each of them individually on getting the best hyperparameters for a set number of trials, and then accessed the top 1 and top 5 with the corresponding validation accuracies, and then used these hyperparameters to rerun a model again for a larger number of epochs.